Hello everyone, my name is Hyunmin Choi from Naver Cloud. Nowadays, data privacy is a very important topic in the biometric recognition area. Thus, I prepared the topic of the presentation as an introduction to privacy-preserving biometric recognition using Hopin encryption. Nowadays, biometric recognition such as fingerprint recognition and facial recognition is used in many areas. It is used for authentication or access control in banking applications. Thus, template vectors from biometric data are extracted by the CNN extractor, and it is used to calculate the similarity between the given biometric template vector and the stored template vector. Biometric template vectors are very sensitive and it is required to be stored securely. Biometric template vectors are highly sensitive and require high-level security to prevent misuse or attack. In this regard, adopting a basic biometric identification method in the cloud presents several security challenges. A notable example occurred in 2015 when approximately 5.6 million fingerprint records were stolen from the US Office of Personnel Management. Moreover, since biometric information does not change through a human's lifetime, these stolen templates pose a significant forensic issue. This highlights the critical need for safe database management of biometric services. Hopin encryption is an encryption scheme that allows computational operations on encrypted data. Hopin encryption is used to protect the privacy of data in scenarios where operations are entrusted to third parties. Firstly, the user creates a public key, evaluation key, and decryption key pair. And the user encrypts the real number vectors with a public key and passes the ciphertext with the evaluation key to the server. The server operates without decryption based on the evaluation key and the result ciphertext received from the user. In this figure above, the addition operation was performed. Finally, when the ciphertext is passed to the user as a result of the operations, the user decrypts the result with his own decryption key. It can be seen that the result obtained in this way is the sum of the two plaintext vectors before encryption. Hopin encryption allows various operations to be performed without decryption. So many studies are being conducted today to apply Hopin encryption to various statistical operations and machine learning operations. In our previous study, BrainTouch, introduced at AAAI 2024, we used an FC layer-based metric. This approach is highly efficient, offering fast computation and low storage requirements. Additionally, it supports flexible scale-out optimization within cluster architectures. However, the FC layer-based metric is primarily optimized for one-to-one matching tasks, making it less suitable for one-to-n matching. In contrast, most biometric recognition architectures adopt cosine similarity-based metrics for one-to-n matching, as they better preserve geometric relationships. The reason we employed an FC layer in BrainTouch was to mitigate the computational overhead of Hopin encryption, which is inherently slow. Implementing cosine similarity in homoping encryption is challenging due to its high computational cost and complex ciphertext management. Homoping encryption-based cosine similarity requires a large number of rotation operations and ciphertext multiplications. However, both rotation and multiplication operations are computationally expensive in homoping encryption. Additionally, the number of ciphertexts increases because extra processing is needed when decrypting and re-encrypting intermediate results, further adding to the overhead. Blind match is a homoping encrypted biometric recognition method. It achieves state-of-the-art time efficiency on homoping encryption-based cosine similarity calculation. Blind match achieves comparable accuracy to plaintext state-of-the-art on both biometric domains. Standard encryption schemes do not support arithmetic operations on encrypted data. So, to calculate the cosine similarity of template vectors, the encrypted template vector must be decrypted to calculate similarity. However, decryption exposes the template vector, allowing potential theft by attackers. The base homoping encryption-based cosine similarity requires many rotation and multiplication operations, which are very expensive in homoping encryption. So, blind match aims to reduce the number of rotations. It makes slightly more multiplication operations, but the total matching time is decreased. The main idea of our method is to split the import ciphertext that contains template vectors into smaller and in parts. The optimized n depends on the template vector size. In this presentation, we will find the optimized n in the experiment. For example, we calculated the cosine of template vector size m. The base homoping encryption-based cosine similarity requires 1 multiplication and log 2m rotations for 1 cosine similarity operation. Blind match requires 4 multiplications and log 2m minus 2 rotations. However, for ciphertext contains 4 times many biometric templates, so the total number of multiplication is maintained, but the number of rotation is reduced. Here is an overview of blind match. It consists of 2 main phases: enrollment and recognition. Regardless of the number of registered users, the client requires minimal network traffic to send the import ciphertext to the server. Moreover, blind match achieves at least 3 times faster identification speed compared to existing homoping encryption-based cosine similarity operations. This is because the template vector is pre-computed and optimized to the ideal size, significantly reducing computational overhead. In enrollment, we use a lightweight bit efficient CNN network such as ResNet 18 that is trained by ARC face loss. Firstly, biometrics such as fingerprint or face image are pre-processed using the special transformer network in front of the base CNN network. And Extracted template vector is encrypted using the user's public key and sent to the server. Blind match requires three types of keys: public key, evaluation key set, and decryption key. These types of keys are generated and distributed to each component. The first is public key. The key is distributed to each client device for encryption. Next is evaluation key set. The key set consists of multiplication key and rotation keys. It is distributed to the server for homepage encryption-based operations. Decryption key. The key is distributed to each client device for decryption. The key is required to be stored securely. When the server receives the encrypted template vector, split it into any parts in encrypted status. The detailed process is: first, the client sends a ciphertext that contains a template vector with size m. Next, the server multiplies the vector mask to the input ciphertext. The mask I are filled with zeros, except for m over n in slots start from L multiplies m over n in the D index, filled with 1. Finally, rotate each part with index minus I plus 1 multiple m over n in slots. The index presents the user's unique identifier. Blind Match adopts two novel algorithms to support efficient and optimized homepage encryption-based matching algorithms. Algorithm 1, called the import ciphertext expansion method, which supports efficient network communication. The client sends only one ciphertext without dependency on the number of registered biometric template vectors. Algorithm 2, called the homepage encryption-based cosine similarity ciphertext cloning method, which supports the total number of rotations. Since rotation is one of the heaviest operations in the CKK scheme, this algorithm can reduce considerable matching time. These two algorithms can support not only optimized machine learning matching time, but also consistent network communication cost. And cluster architecture. Blind Match supports cluster architecture. Blind Match uses a scalable cluster architecture with a main server and multiple cluster servers for parallel processing of encrypted ciphertexts. Since the number of registered biometric information changes depending on the situation, we adopt the cluster architecture for flexibility. The next is compression method. The compression method is an efficient method that can combine the multiple result ciphertext as one ciphertext. We adopt the compression method to reduce the communication cost between the server and the client. Here, we introduce our two research questions. Research question 1 is: how many times more efficient is blind match compared to the conventional homepage encryption-based cosine similarity operation? Research question 2 is: what is the optimal template vector size that maximizing efficiency while maintaining accuracy against the state-of-the-art model? Here we introduce the evaluation. The first is homepage encryption parameter specification. We utilize Latigo version 5 and an open source for homepage encryption with ring degree n is equal to 8192 and log PQ is equal to 158 to ensure the 128-bit security level. The conjugate ring supports 2 times more number of slots than the standard ring setting. A ciphertext can contain 2 times more floating numbers than in the standard ring setting. It makes more efficiency. Next is server specification. We constructed the client server architecture. 1 client, 1 main server, and 3 clusters, each equipped with 2 cores and 8 GB of RAM. The next is CNN model specification. We employ ResNet 18 for the template vector extractor, which is denoted as R18, and the CNN model was trained using the arcface loss function to enhance its discriminative power. We use expensive public fingerprint datasets and fingerprint datasets and facial datasets. The detailed dataset is introduced in this page. We use 5 facial datasets and 4 types of fingerprint dataset. The execution time of blind match is introduced on this page. We conducted the front and in on 6,144 IJBC samples with the following parameters. Ring degree n is equal to 8,192 and I is 3, and template vector size is equal to 128. L is equal to 3, and our experiment shows that the total matching time is smallest when the n in is equal to 4. In this experiment, we get the optimal template vector size. We evaluated them on 6,144 samples over 10 trials. Values in parentheses represent the standard deviations. With template vector size of 16, 128, and 256. On figure 1 shows the mean of 1 to n matching time. The base means the conventional homepage encryption-based cosine similarity operation. The result shows that the matching time is linearly increased when the template vector size is increased, and our architecture is about 3.5 times faster than that of base with template vector size of 128. In this experiment, we evaluate the accuracy of 1 to n matching. Maintains comparable accuracy without a significantly degrading performance. We use the base model as cosine phase loss and ResNet 50 and template vector size of 520, which is a defect in the biometric area. Even with a small template vector size, there is a slight decrease in accuracy. The reduction in computational complexity results in faster execution times. Usage of 128 template vectors with blind match hoping encryption technology is recommended for most facial recognition models. The result shows that the accuracy is proportional to the template vector size, but the computational cost is increased when the template vector size is increased. So we recommend the template vector size 128. It supports high accuracy with optimized matching time. In this experiment, we evaluated the accuracy of one-to-one matching. Even when reducing the template size from 512 to 16, there is minimal loss in accuracy. For the blind match fingerprint biometric service, we recommend using 16 template vectors. We set more difficult environment by combining low-quality FVC datasets. FVC dataset-based experiment shows that our performance degradation compared to clean inputs from the PolyU datasets. The result shows that the template vector size 16 supports a high accuracy. So we recommend the template vector size 16 in the one-to-one matching tasks. We evaluated the accuracy of one-to-one matching with various state-of-the-art methods. The evaluation is conducted using the PolyU contactless fingerprint dataset. The 5 methods are non-encrypted methods, and blind touch and blind match are home encryption-based methods. We evaluated the AUC score and EER score. The result shows that blind match supports high AUC and EER scores. Here is the deployment plan of blind match. First, our proof of concept implementation demonstrated blind matches exception efficiency, matching over 5,000 face images and performing 6,144 identifications in just 0.74 seconds across multiple biometric modalities. This establishes blind match as the first real-time whole-pig encryption-based architecture for one-to-N biometric matching with practical applicability. Next, we will deploy blind match in real-world scenarios, expanding its functionality to Android devices via a cloud-based matching server. To evaluate performance and scalability, we plan to implement blind match in a large research institution's entrance system serving over 4,000 employees. Here is the conclusion of this presentation. The conclusion is described on this page. First, an efficient and privacy-preserving whole-pig encryption-based biometric one-to-N matching architecture. Next, design a new whole-pig encryption optimized cosine similarity algorithm. We provided more than 3 times faster than conventional whole-pig encryption-based cosine similarity, and we overcame the whole-pig encryption's computational avoid challenges. Third is demonstrating superiority via extensive experiments. One-to-N fingerprint identification, also facial one-to-N identification. Finally, blind match is the first study. A home encryption-based biometric service on both face and fingerprint domains. We shows that a further possibility to apply it for other biometric services. And we release the source code and pre-processed data sets for reproducibility. Thank you.